resistance at all. So let's look at when we do have resistance. So we know we don't have an ideal inductor. It's going to have some resistance. So in this situation, when we have the switch there in position A, we are going to charge up the capacitor to that EMF, that voltage of that source of EMF. Then we're going to move our switch into this B position, and we're going to write a loop equation for what happens here. So once we're in this position B, let's write a loop equation. So I'm going to go around my loop. Doesn't really matter which direction I go. This, I guess, makes the most sense. And as I go around the loop, that loop equation I write is going to involve the EMF through my inductor. So that's, resisting any change in EMF. We had no current going through it before, and now we do have current going through it. The voltage lost across my resistor, and the voltage across my capacitor. And that gets me back to my starting point, so I can say that that equals 0. So again, I'm going to say that my current is going to be related to the charge that comes off my resistor. So it's losing charge from that positive plate. Sorry, not my resistor. Losing charge from the positive plate of my capacitor, rather. So if I rewrite my loop equation now, I've got something that looks like L second derivative of Q with respect to T. Then the first derivative times R, and then my original function times 1 over C. So this is what's called a second order differential equation because we've got a second derivative. I do not expect you guys to have differential equations under your belt necessarily just yet, but it looks like one that maybe we saw before. So this looks like a second order differential equation that has a similar form to this one. So I've got mass, I've got position, all that good stuff. This equation is for the damped harmonic oscillator. So it is always our intention to get to simple harmonic motion, including damped harmonic oscillators in Physics 1, but that is not necessarily what happens. So if you haven't seen this before, that's okay. But just know that we've already solved this. So if we have already solved an equation that looks like the thing we're trying to solve, we can take this solution and apply it to the equation we're trying to solve. That is one of the beautiful things about seeing something that looks familiar. So if we've already solved it, what we're going to get is equations that look like this. So here we've got the solution to that equation. That is our solution to our differential equation that was on the previous page. And in this case, we've got an omega with a subscript d. That is this omega. So it's related to 1 over LC and r over 2L squared to the 1/2 power, which just means square rooted, right? So that is a messy thing to write inside the cosine. So we just give it a new name, and it's our damped oscillation. So what's going on here is that this exponential is what's giving you this downward amplitude. So it's reducing the amplitude of your cosine function as time goes on. And meanwhile, this cosine function is what's giving you that oscillation as time goes on. So this is a damped harmonic oscillator. There are 3 types of damped harmonic oscillators that we could talk about. So let me give you the 3 types. There is first the underdamped oscillation. So an underdamped oscillation, what that does is pretty much what this picture is. It oscillates a whole lot before it reaches that steady state at 0. So underdamped oscillators for this situation are going to have a relationship where R squared, our resistance squared, is going to be less than 4L over C, right? So that is relating to what this looks like as far as our frequency of oscillation, or angular frequency, and it's also related to this exponential, right? So that's our underdamped case. Then you've got critically damped. So critically damped just means that it is just right. It's going to reach 0 at the shortest amount of time. And so you are going to see something that's a little more like that, right? So critically damped situation happens to be when R squared is exactly equal to 4L over C. That'll give us our critically damped case. It reaches 0 in the shortest amount of time. And then you've got overdamped. So you can guess what overdamped is going to be in this case. Overdamped is going to relate, our resistance is going to be larger than 4L over C. And for our overdamped case, what is going to happen? It's not going to oscillate, but it is going to take forever to reach 0. So it's going to be like that door that swings shut very, 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 very slowly, right? So this omega D is for our underdamped case, where R is less than the square root of 4L over C. Okay? So we're going to look at those. And again, you could add in a phase constant here if you needed to. So there are, because these are similar types of equations, they're similar types of differential equations, you can actually talk about analogies between the RLC circuit and a particle in simple harmonic motion, right? The charge is like the position, current is like velocity, and on and on and on. So this is where we got that we could use our solution for our damped harmonic motion to talk about how the charge moves back and forth in this circuit. So it oscillates if we've got the right relationship between R and L and C. So let's look at an example with that. So here's an example of damped oscillation. So at t equals 0, we have a 40 millihertz inductor placed in series with a resistance of 3 ohms and a charged capacitor of 4.8 microfarads. So this is going to be our L that we're given. We've got an R and a C. It's charged up, so we know this is like the example or like the information that I just gave you. So first we want to show that this circuit will oscillate. So what that's asking us to check is to check the relationship between R squared and 4L over C. Now remember, if we look back at what we were just talking about, when something is underdamped, it will oscillate. When it's critically damped, it will barely oscillate, and it will reach 0 in the shortest amount of time. And when it's overdamped, it will not oscillate. So we want to check R squared versus 4L over C. So R squared, we're just going to take those 3 ohms and square them. 4L over C, we are going to take 4, and we want to make sure we're in the right units. So 40 millihenries is going to be 40 times 10 to the minus 3 henries. And over C, that's going to be 4.8 times 10 to the minus 6 farads. So this actually gives us, if we cancel out all the units and look at our unit relationships, this should give us, let me find it here. This should give us 3.3 times 10 to the 4th ohm squared if we cancel out all the units correctly. So in this case, if we compare, I guess I never wrote this, my 9 ohms squared on my R side to something that's times 10 to the 4th, that is definitely in our underdamped case. So if we're underdamped, we definitely oscillate. So we can say check, we've checked that it will oscillate, we've done that one. All right, part B says determine the frequency of oscillation. So I gave you an equation to use for frequency. In your book it has the subscript d, so it's omega d. That is the angular frequency. So we have to remember that angular frequency has this relationship to frequency. So when they say determine the frequency, because they haven't given us that extra word angular, they're telling us to determine the F, not just the omega d. So omega d, let's start with that equation at least, is the square root of 1 over LC minus R squared over 4LC squared, right? So there I just distributed my squared in that equation, and we're taking the square root of all that stuff. So again, we want to use that R equals 3 ohms, that L equals 40 times 10 to the minus 3 henries. So we want to make sure we keep in those factors of 10 and don't lose them in this adventure. And C equals 4.8 times 10 to the minus 6 farads. And so we want to put that inside parentheses when we square things. And then to find our frequency, we need to divide by 2 pi to find our linear frequency. And so when we divide that by 2 pi, we're going to get something in the neighborhood of 3.6 when we round, times 10 to the 2, and this would be in hertz or in 1 over seconds. So part C, we want to find what is the time required for the charge amplitude to drop to half its starting value. So if you remember, our charge equation looked something like Q equals our maximum Q times an E to the negative R over 2L times T, and then we've got a cosine function here, and maybe even a phase function, although I didn't give that to you in the last one. And because our capacitor's charged up when we start, that equals 0. So we've got cosine of something with a T, and we've got this exponential function. So which do we actually use here? So we want to know when it's dropped to half of its maximum value. So we can see we can divide out a max, and we've just got this. Right? So what I'm going to argue is that we really want to look at where the exponential function drops to half and not pay attention to the cosine function. And that's going to give us our best approximation for where the charge amplitude drops to half of its starting value. Right? So we're looking at the amplitude, not just the charge. So that's telling us to look back at that exponential drop that tells us about the amplitude. Right? So again, we've got our t that we're trying to find that's up in the exponential, so we want to take a natural log and rearrange things. So we're going to take a natural log and have negative RT over 2L, natural log of 1/2, which is the same as saying the natural log of 2 with a negative sign. So we're going to say that t, and these negative signs cancel each other out. Looks like that. So 2L divided by R times the natural log of 2. And when we plug in the numbers that we have, I'm going to get something in the neighborhood of 18 milliseconds as my answer. So that's the time required for the charge amplitude to drop to half. And this is my argument for using my E, because we're talking about amplitude. Our final thing in this example is to find what value of R will make the circuit non-oscillating. So we want to go back to our definitions of critically damped. So critically damped, we're going to call that non-oscillating. And even overdamped would be non-oscillating, right? That would definitely be non-oscillating. So we basically want to find the regions where R either equals the square root of 4L over C, or R is greater than the square root of 4L over C. So all we really need to do is find what the square root of 4L over C is, right? So I'm going to put in, oh, it's kind of redundant to write. I'm going to put in the square root of 4L over C. And that was in henries, that's in farads, so everything should cancel out. And when we take the square root of that, we should get in ohms about 180. So if R is greater than or equal to 180 ohms, we will have a non-oscillating circuit. So that's our example of RLC circuits. They're pretty useful. Your differential equations professor, if you have to take that class, will definitely love them. And you'll see them again, I'm sure. Those types of equations are pretty normal in physics and engineering. So I will stop there. That is all of chapter 32, and we'll pick up with AC circuits next time.